Monday. We're very excited to have you here. Thank you very much for everyone that is watching us through Zoom and through Twitch and through YouTube as well. I have here with me today Tatiana Gabruseva and Vincent Warmerdam, and also Kevin, the director of Python Ireland. Hello. Perfect. So we're going to start tonight with Tatiana's talk. And Tatiana is a data scientist. She is also an artist, a machine learning and computer vision engineer. She has a doctorate in physics, and who knows what else. I had the honor to be her session chair for last PyCon Ireland in November last year. And here we are again talking about Python for computer vision. Well, welcome, Tatiana. Thank you very much for coming.
Thank you very much for having me. So my talk today is introductory talk about Python for computer vision, mainly for those who are not that familiar with computer vision itself, but is keen on data science and computer vision in general and work with Python. So, So what is the computer vision? In the computer vision, we want to make computers see. You can see a volley here, and you can see it has two cameras. So nowadays, we have cameras everywhere. We have smartphones, baby monitors, security cameras, infrared cameras, LiDARs, etc., etc. And every single second, we produce a lots of video information and record it, every one of us. So having all that vast amount of information, we are trying to analyze it and make sense of it. When you look at this picture, you can see straight away that here is the girl, here is the cat. You can see this is the face of the girl, and you can see how happy she is. And the cat, I'm not so sure. So what we mean by computer vision, it's making computers to gain that high-level understanding from vision, from images and videos, just like we do. And this is not an easy task, because vision begins with eyes, but it truly takes place in the brain, here in the visual cortex. And it took Mother Nature about 540 billion years to accomplish that task. And a lot of that time actually went into the development of the visual cortex, not the eyes itself. So by seeing, we really mean understanding. And in computer vision, we are trying to make computers to gain that high-level understanding from images and videos. This is a complex task, and it can be broken down into smaller tasks. So the computer vision tasks are classification, when you identify what is that on the picture, you see people. Identification, who exactly is that? What this person? It's Uma Thurman and John Travolta. Object detection, where is that? You detect people. Segmentation, where exactly is that? You detect masks. You can do pose estimation, like, and what are they doing? They're dancing, action recognition. And finally, you can do a scene understanding. What is really happening? A man and a woman is dancing. So those are the typical computer vision tasks. And why is that so important that there is a big fuss about it nowadays? Computer vision has a lot of great applications. It can be used in biomedical applications to classify cancer histogram and also select individual cells in the histograms. It can be used in self-driving cars because the self-driving cars rely a lot on the LiDARs and cameras to gain information around them and to detect different traffic objects, other cars, road signs, traffic lights, and so on. It also can be used in the security to identify any potential hazards and for action recognition. It is used for satellite imaging to detect fires and also find people who can be lost from the drones. And it actually even has applications in art when you can transfer different styles, like here you transfer Van Gogh on some photo. And also for the automatic animation and to make movies like WALL-E easier. And it has important applications in medical diagnostics. The computer-aided medical diagnostics becoming more and more popular for a number of crucial tasks like pneumonia detection, anomaly classifications, and different organ segmentations. So the computer vision is quite a wide field, and it has a great importance for us, mainly because there are also visuals, like around 30% of our brain works on processing visual information. So therefore, it's not a surprise to us that computer vision becomes an important field nowadays. And we want to advance that field, so we want to make computers see so they help us to see better. And let's consider one example. In the famous cartoon WALL-E, there is a robot Eva who comes on Earth with a mission to find a plant here. So basically, let's program that Eva. Eva has a classification problem. Eva has to define, is it a plant that she sees, or it's something else like a can? How we are going to teach Eva to do that? We are going to teach Eva exactly how we teach children. When we teach children, what is that? What are the different objects? We show them the object and we name them. We say that this is a tree, and this is a cat, and this is a flower, and this is a can, and so on. So we do exactly the same for the computer program. We show different examples of different images, and with the labels, we name those different objects. So first of all, we need to get a great amount of data. Basically, children by the age of 3 are able to identify most of the objects around them. But by the age of 3, they have seen lots of bicycles, cans, and plants. So to get that vast amount of information, the ImageNet dataset has been created. And it has now 15 billion images with around 22,000 categories. So you can go to the imagenet.org and type, let's say, a tree, and you will have a lot of examples of different trees. So you can download the data set for free, and you can use it to train your computer vision programs. Let's now consider how is it working. Basically, what is an image from a computer point of view? An image is a set of numbers, basically. It's an array of different numbers that corresponds to the pixels intensities. And it has 3 channels, red, green, and blue. So you actually send a 3-dimensional array to your program. And then you send a label, let's say it's a tree. And then you have some machine learning algorithm. And what you want to have at the output is actually the corresponding label, let's say it's a tree. And the particular family of machine learning algorithms that work well with these kind of tasks actually are neural nets. So the neural networks were inspired by our biological neural nets in the brain. In the brain, we have a lot of neurons that get connected with other neurons and then transfer information further to the next neurons. And in artificial neural nets, you have neuron-like unit that gets inputs from the previous units, summarize it, apply some nonlinear function, and pass it forward. So it has some similarity with our brain. And in the neural network, artificial neural network nowadays, we have about 24 million nodes. It depends highly on architecture, so this is just an example to give you an idea. It has about 140 million of parameters and lots of connections. And in the true biological brain, you have much, much, much more than that. So basically, you send that input array, which is your image, to your network, and it propagates through it, through all these neurons, from layer to the layer, and then you get some output. So in the beginning, you get wrong outputs. The program is guessing something. Let's say it is guessing it's a cat. And then it compares its guess to the true label, because we also send a true label. We say it's a tree. And we defined a mismatch between those true labels and the outputs. And those mismatch we call a loss function. The loss functions can be defined differently. And there is a whole course which explains that in details of about gradient descent and optimization of the loss function. Is the course of deeplearning.ie of Andrew and G. In that course, you can see that in details, but in 2 words, you actually minimize those loss function by tuning your parameters of your model. I will explain it in a bit more simple way. Let's consider your neural net as a set of different parameters that you can tune. And it reminds me a bit of the guitar tuner. Basically, I like to play a guitar, and from time to time I take it, and it's always not tuned because I don't play often. So when I take a guitar, I basically start my guitar tuner, and I pull the string, and it tells me, no, this is wrong. So then I tune a bit of parameters, and I pull the string again, and again, and again, until my guitar tuner is happy, and then I see that this string is tuned. So likewise, we are doing similar in the computer vision architectures. When we tune them, we a bit tune the parameters of that model to make sure that the output of the model corresponds to the true label. So once we've done it, we also need to validate our model. We do it by sending the unknown image that the model has not seen. Let's say it's a cat. We don't send any label, but we know the label of that image. We propagate an image as a race through the model nodes, and then we look at the output, and hopefully we get a cat. So if on validation we get right results as we expect, we are ready to send our model to the wild. So we are sending our EVA to test environment to find that plant. So this is an easy example how it all works in general. It is common to implement such problems using Python. Python is a language of machine learning nowadays, and there is a good reason for that. Actually, Python has a great number of deep learning frameworks. It has Pytorch, TensorFlow, Keras, etc. And it also has a lot of helping libraries. It has libraries for processing images, library for augmentations, for working with the arrays, and so on. So it has all those tools ready for you, so you don't need to write everything yourself. And this is very convenient. So by using all those tools, I'll show you how to make some easy peasy pipeline for classificator. First, we'll need to get the data. We will not use ImageNet because it is huge, but we can use a smaller data set with 10 classes like CFAR. And we will use Pytorch for this example. So in Pytorch, you already have the data set. So you can simply import the data set just in 2 lines, set train set, CFAR, and test set. And then you can do the data loaders also in 2 lines. The data loaders basically send your images with your labels to your program. So this is done here in these 2 lines. This is easy. Then we do preprocessing of the data. Very often we want to rescale our images, resize them, and maybe augment them. So there are libraries for them. With openCV, you can easily resize images and do certain modifications to them. And with augmentations library, you can easily augment images. Why do we need it? Because in wild, you can see different variations of the parrot or the cat or whatever is that. You can see it from different angle, under different illumination condition, under different zoom. And it's important that your program is ready for that, that it has seen all those variations. So augmentations of images help you to create the different variations of a single image, and hence to help your model to generalize better. So using augmentations is also very easy. Just you set the transforms that you want to use, let's say horizontal flip, random crop, and so on. You compose them together, and then you just apply them to your image in 2 lines. After you have data preprocessed, you need to set up the model. Again, in the torchvision library, you have already all popular architectures. Those architectures that you don't have there, you can find on papers with code, and often they will have their code in Pytorch as well. So then, just to import model, it's 2 lines. You just import it from models, the models that you want to use. Here, the pre-trained means that it already has been pre-trained on ImageNet. Many architectures available online now have their weights already pre-trained on ImageNet. This is very convenient. So then you need to choose your loss and an optimizer. So for the multi-class classification, we will use cross-entropy loss, which is a commonly used loss for this task as a criteria. And we can use Adam optimizer, a number of different optimizers. So Adam usually works fine. So that's what we will use. Again, we also import it in 2 lines. Everything is written for us in Torch. And basically, the optimizer is making your gradient descent algorithms that I was talking about. In the validation, you use just the data from the test loader. You calculate the outputs from the model, and you see some metric. Here we will see, let's say, accuracy. You see how well your model is predicting what it's supposed to predict. And looking at your training loss and your training metrics and your validation metrics, you can make a decision when to stop training of your model, or if you need to change something to make your training better. So that's it, basically. That's how you train the model. And it gives you this illusion that the Pytorch is simple and it can be explained in 5 minutes, because I've done it like in 5 minutes. Or there are a lot of tutorials online that tells you that you can learn TensorFlow in 5 minutes or something like that. But this is all an illusion, of course, because in real world, things don't work like that. This was very easy example, just to give an idea. In the real world, we have a number of problems. We have occlusions when the object that you want to detect is hidden. We also have different poses. So you didn't expect that, and your cat didn't expect that, and for sure your model didn't expect that. So when it gets, it probably will make an error. You also have intra-class variations. You have different illumination conditions, and you just may have some confusing images that are hard to identify. So all those problems we meet, and especially in medicine nowadays, let's say we have now pneumonia detection, and we think it's a pneumonia, but actually it isn't, because this is a pneumonia. It is very hard to bring great accuracy in medical applications for some reason, because it's very hard to label those data. Basically, you need a consortium of experts to label that kind of data. You need like 8 radiologists to agree where the pneumonia is, where it is located. And obviously labeling such data is very expensive and it's time consuming. So therefore, we don't have that much labeled information still in medical field. It is growing every day, so, and in 5-10 years, I think we will have a lot of data, but still nowadays, the medical data sets are quite relatively small. And there is some disagreement between radiologists who label the data itself. So we deal with noisy labels, and there are ways to deal with that as well. So in the medical field, it is growing and it will be there, but it's important to understand the limitations as well. Therefore, augmentations are very important. So when you don't have a lot of data, it's easy to overfit your models because they have so many parameters. so one of the ways to deal with that is to augment a single image many times. Like here you have one single image just augmented many times. And then you send all those variations to the program. And those are the references with important resources for those who want to learn more. There is a nice course, Stanford course, computer science class, and the deep learning course on Coursera by Andrew Ng. I also like lectures by Lex Friedman from MIT. And you can also see tutorials on Pytorch, as well as you can see tutorials on Keras or TensorFlow, or whatever framework you will choose for your task. So this is how Python is used for computer vision problems. That's it. So if you have any questions.
Oh, perfect. Well, thank you very much. That was super cool. Well, I have the question we have in the Q&A so far is someone asking about the availability of the slides. And I can say that we will put the slides up on YouTube as soon as we put as soon as we upload the talk. It's gonna be there. Yeah, anyone else for questions actually? Because I have one. Okay.
I know I have one there. Hi there. Thanks for a great talk. Just a quick question, actually. Something I'm very interested in. You mentioned LiDAR, and previously we had a presenter give a talk about Earth observation. So using computer vision technology with our Earth observation data, have you any background with that or any observations with that?
I deal with, there is a SpaceNet challenge when you have satellite images and you need to segment, let's say, buildings. So I work with that, but it's, yeah, so basically, what is the question about that? Because it's like different domains, like you can use LiDAR, radar data, you can use images, you know, RGB data and.
Okay, no, that really, the question really was just to sort of expand upon that. I think it's just a very interesting subject.
It is, so basically it has many domains, like recently I was working with SpaceNet challenge. So basically what they do, they observe different buildings from the sky, sending, you know, drones, but the weather conditions can affect the vision a lot, so you don't see anything if there is cloudy. However, there are radars that can go through the clouds. So, and then nowadays they're kind of making it multimodal. So they take photos with cameras when they can, and they also send radar, which is noisy data. The accuracy is lower, but it can go through any weather. And you are trying, basically, I was working with those radar data. They're weather independent, but the metrics drop a lot because it's noisy. It's not that you know, it's not that clear to see compared to images. And so now they're trying to make it like multimodal, putting all the modalities together, let's say, and you can segment roads and you can see the buildings and so on. The particular applications of that, you know, there are obviously some military applications, but I like more peaceful applications. One of the important applications of the satellite imaging is detecting fires. If the fire is somewhere, something happened. And one is, I know the team who is working not exactly detecting buildings, but they send the drones above the forests. So when people get lost in the forest, their relatives trying to contact some, you know, source companies, and they send the drones in those remote areas. And from the drones pictures, you cannot physically see that many pictures as a human, you will miss it. But computer program is trying to see if there is a person in it, you know. And of course it's in remote areas like where, you know, some expeditions go and so on. So there are applications like that, yeah. It's kind of progressing. But the weather is important in there. So nowadays they are trying to use radars to overcome the problem with clouds and the weather conditions. That's what I know.
Good stuff.
Cool. Cool. Wonderful. So we have another question, this time from Asmir. So Asmir is asking if you have any thoughts on cloud computer vision, like Amazon Recognition versus Google Cloud Vision.
Basically, no, I did not work with those kind of ready. It's like ready solutions, right? So it's basically when you. No, I developed my own algorithms, so I cannot elaborate on that.
Okay, perfect. Okay, no problem. Then I have one last question then. Well, I think it's one last question, but I have a question for you as well. So you were talking about computer vision being used for medical diagnosis. Then recently, when the whole coronavirus outbreak started, we had that hype with that guy that was able to write a algorithm that he claimed was like 97% accurate on detecting COVID. Yeah, exactly. So what's your take on that?
So basically, well, like in 2 weeks, in 3 weeks, I'm having a CVPR talk. CVPR is a big conference on computer vision. It's going to be remotely in Seattle.
Okay.
And I have a workshop about computer vision for automatic pneumonia detection, which I happened to make last summer before coronavirus, just, you know, it wasn't planned. So I worked on pneumonia detection, and before that all started, basically, impossible. So, and I'm having my talk I can repeat here as well, maybe, but it's very, you know, it's very specialized. So it's for, not for the beginners in computer vision, it's more specialized. So, and in this work, what we did was pneumonia detection. It was pneumonia detection challenge on Kaggle back in 2018, before it all started. So basically, to classify pneumonia from not pneumonia, you indeed can get like 98%. This is not lie. But not every pneumonia is kind of viral and caused by coronavirus. And not always coronavirus can cause a pneumonia. So I talked to people who work with basically one of my co-authors, because we worked on this pneumonia detection. We published a paper. It went to archive. It will be published on CVPR proceedings, and he was contacted in relation to the problem with coronavirus. And they have now there are two modes you can work. You can go with chest X-ray or KT diagnostics. So KT is different scans, you know, when you scan your lungs, like not just making a chest X-ray, but you have different scans, pictures of different scans. It's like 3-dimensional. And so basically the KT is much more accurate. And so that what I've heard from people who work with that sometimes on chest X-ray you don't see pneumonia, but on that KT you have pneumonia. And your test for COVID can be positive. You don't have pneumonia on chest X-ray, and you can have pneumonia on KT. Things like that also happen. So with COVID, thankfully, most of the people don't develop pneumonia at all. You know, it's also complicated. It's only complicated cases. So I would not mix those two. I think people are trying to a bit, you know, using the hype. So pneumonia detection is pneumonia detection. Pneumonia is pneumonia, not always caused by COVID, and can be different. It can be bacterial pneumonia, can be viral pneumonia. It can be different origin itself. So I wouldn't mix those two conditions. And if you write that you have algorithm for detecting pneumonia, it is not equal to algorithm for detecting COVID. I have algorithm for detecting pneumonia, in fact. So it's I'm going to talk about it in 3 weeks then, CVPR. So, it's just not the same. And when people write all this, it's a bit, yes. Plus, many of them, they used a little bit of data. For instance, in that challenge, I changed data on the data from 25,000 patients. And it's not that much, to be honest, but it's 25,000 patients. That's what we made for the paper on pneumonia detection. And people who write it on LinkedIn and everywhere, they use that open data set with, I don't know,
70 people, I think. Yeah, yes. It was a ridiculous amount.
That's just definitely, you know, you just learn when you have, you know, millions of parameters and 70 images, you just remember them. That's it. So absolutely not, you know. But yes, I was thinking about getting the programs that we made earlier before the COVID. It was for different pneumonia because COVID caused, you know, viral pneumonia. I think the data that we had was a bit different pneumonia. But anyway, trying to run an inference on the programs that we already changed on COVID data. So I had this in plan. So we'll see if I can find a time to make it. So.
Okay, cool. Okay, wonderful. So I have one more question for you, and it's going to be the last one. Then we're going to go for a break, and then we come back with Vincent. Mikale is asking, what are the main challenges when productionizing the data science solutions, for example, medical ones? How to monitor, observe the performance of the models? Do you have an experience with that?
Yes, so basically in medicine, there are different production areas, like you can have medicine, you can have production on devices and so on. So all those have different challenges. So I had some experience with for devices. So basically in devices, it's easy for you to train a program and make an inference having unlimited computational resources. However, in practice, when you work, let's say, in the plant, you want that inference to be run on some tablet or on iPhone. And so then you need to basically make sure that your program, which can be huge in size and so on, goes into those limited computational resources. So one of the challenges is to make it compact, and there are ways to do it as well. So the second challenge, most important challenge, is to make sure that the data you will have in test, you have them for your validation at least, because often people are training programs, you know, on some artificial data or maybe not sufficient data, and then in test it has encountered something new and your program does not work. So it's important to collect the data, enough data in the real environment that will happen in application. So if this is going to be run in the plant, you need to tell people in the plant to take pictures exactly how they will be taking it every day, because you can generate a lot of artificial data or find some relevant data set and train your model. But it's important to have a lot of enough data which are as close to your test environment as possible. And then your program should be robust, because if one day the procedures will change and then will take different images, your program can just stop working. So therefore, the main challenge, I think, is still collecting the data for real environment as close to your test environment as possible. This is the main challenge. And then, of course, make it compact, make it running, deployment of the model using limited resources. So this is for production field. In the medical field, you can wait. In the medical field, if you have a scan, you don't have to have immediate answer. You can wait for the model to take a minute or even more. So you can use more time. The computational resources is not an issue in medical field. In medical field, it's still important to get the data, just like you will have. And it's important to get them labeled, because it's very expensive. You need a lot of experts to label them. But the most trouble in medical field is to make it usable by doctors, because doctors, they're busy people, they have their procedures already in place. They're used to certain protocols, and it's not that easy to go and intervene in their work, and it shouldn't be easy. So basically, to bring some computer-aided diagnostics to hospitals, you need to make a deployment in line with the medical procedures for the doctors. So you need to basically not just give them a computer program, you need to give them a device that will send, green light or red light and orange light if there is, like, it's not sure or something. It has to go in line with the medical protocols. And I think this is the most challenging. You need to communicate closely with the doctors to make that happen. To see how they work every day, how to introduce it in their everyday routine. So the challenges are completely different for those two fields.
Okay, perfect. That's great. Wonderful. Well, thank you very much, Tatiana. It was an absolute pleasure. Thank you very much. That was a really good talk. We are going to take, let's say, a 3-minute toilet break, and then we come back with Vincent and some chatbots. Thank you. Thank you very much.
Thank you. Thank you.